Hello, everyone. Today we're going to talk about binomial probability distributions. By definition, a probability distribution results from a procedure that meets these requirements. The procedure has to have a fixed number of trials. The trials must all be independent, meaning each trial does not affect the next. Each trial must all have outcomes that are in two categories. These are typically just success or failure, yes or no, something like that. The probability of a success remains the same in all of the trials. So that's why we call it binomial. There's two results, success or failure. Some notation we're going to use. We're going to typically use S and F for success and failure. It might not actually mean success and failure, but just for notation wise, we keep it to S and F. So success doesn't always have to be a good thing. The probability of success is equal to P, and the probability of F is the same thing as the complement, so 1 minus the probability of P, which we'll call Q. N is the number of our trials. X is a specific number of successes in N trials, so X can be any whole number between 0 and N, including N. It could be equal to N. P is the probability of success in one of the N trials. Q is the probability of failure in one of the N trials. And the probability of X, or P of X, is the probability of getting exactly X successes among the N trials. So we might see all of these different pieces of notation. Right. So I mentioned this a second ago, but some cautions. The word success is used arbitrarily here. Does not mean it has to be a good thing. Success just means is used for our notation in our formulas here. Success in a trial does not mean it has to be good. We always want to be sure that X and P are consistent in the sense that they are both refer to the same category as being a success. We'll normally keep pretty certain here, so that's not a big deal for this class. But let's look at an example. When an adult smartphone owner is randomly selected, there's a 5% probability that this person is cashless, meaning when I say cashless, they never carry cash. We want to find the probability that among 10 randomly selected adults, exactly 2 are cashless. So first, does this procedure result in a binomial distribution? Yes, they either have cash or cashless. That's two choices. All right. So now we wanted to identify N, X, P, and Q. So N is our total number of trials, which means we're asking 10 random people. So N would equal 10. X, we want to find the probability that among 10 randomly selected adults, exactly 2 are cashless. And then P and Q are our probabilities. So our probability of someone being cashless is 0.05, which means the complement is 0.95. So let's look at a more specified solution here. So I kind of said it shorthanded on the last slide, but first, this procedure does have everything that we need for it to be a binomial distribution. So that's what we're answering first. So we have a fixed amount of trials. So that's good. The 10 trials are independent. We're picking a different person each time. Definitely makes it independent. So that's good. We got independence. Each of the trials has 2 categories. This is the one I highlighted before. 2 categories, so it's binomial. And then for each randomly selected adult, every time there's a 0.05 probability. We have everything that we need for a binomial distribution. Okay. And then we identified our variables. We have 10 randomly selected adults. So we said n was 10. We want to find the probability that 2 of them were cashless. So x is equal to 2. And then the probability of success was given 0.05. So this is a little wordy because it's the probability of being cashless. So the probability of not having cash is 0.05. So that's the way it was worded. So our probability of P is 0.05. So that means the probability of not P, so 1 minus 0.05 would be 95, 0.95. Okay. So we have a formula for probability, binomial probability. So probability is n factorial divided by n minus x factorial times x factorial times the probability of p to the x times q to the n minus x for all x from 0 to n. So this is the specific formula. We won't use computations using it, but this is if I wanted to do it by hand, I could use this formula. But let's do one example just to see how it looks like. I won't ask you to do this on your own. We may use technology to do so, but I won't make you use this formula. I just want to demonstrate it one time. So we have everything from the slide before, same example. N, X, P, and Q are all the same. Let's actually find this probability now. So given our formula that I just gave you, we're going to plug in the numbers that we found before. So if we plug in these numbers, 10, we're plugging in n. So 10 factorial, 10 minus 2 and 2 was our x value. P was 0.05, Q was 0.95 squared, and then n minus 2. So we're plugging in our x and n minus x. And then once we have everything plugged in, we're going to just slowly compute this. So in step 1, we'll do just the parentheses of the first one. 10 minus 2 is 8. 0.05 squared is 25 thousandths. And 0.95 to the 8th power is 0.663420. So we have 10 factorial divided by 8 factorial times 2 factorial. So if we do 10 divided by 8 factorial, a little trick we can do is factorial means for 10 factorial, 10 times 9 times 8 times 7 times 6, and so on. Those are all the same numbers as 8 factorial, except for the 10 times 9. So 10 factorial divided by 8 factorial is just 10 times 9, which is 90. 2 factorial is 2. 9 divided by 2 is 45. We multiply these three numbers together, and we get 0.074635, and we're going to round to 3 digits here. So this is saying there would be a 7.46% chance, or 0.0746 probability. We have a few more formulas here. It's a little bit easier to use P and Q. So to find our mean, mu is equal to n times P. Variance is n times P times Q. Standard deviation is just the square root of that. And our range rule of thumb still is always going to apply. Significantly low values is the mean minus 2 standard deviations. Significantly high values is the mean plus 2 standard deviations. And then anything between those ranges aren't significant values. Right. So let's look at an example. So we have n equals 460 overtime wins in NFL football games. We get probability of 0.5 and probability of 0.5. assuming winning overtime coin toss does not have an advantage, so both teams have the same chance of winning the game in overtime, which is a probably large untrue assumption. These are definitely not equally likely. Both teams do not always have an equally likely chance of winning in overtime, but for the sake of this problem, let's assume that teams have an equal chance of winning in overtime. So we're going to say they're both 0.5. So we have an N and P and Q. We want to find the mean standard deviation in groups of 460 games. Then we're going to use the range rule of thumb to find the values separating the number of wins that are significantly low and high. And then we want to know, is the result of 252 overtime wins in 460 games a significantly high number? So take a second, pause the video, and I want you to try and write this one out. And then we'll go through it on the other side. Remember, we have these three formulas and then our range rule of thumb we can use to answer all the questions because we have an NP and Q. Let's take a look. So we have NP and Q defined, 460, 0.5, and 0.5, and we can apply the formulas. Our mean is just N times P, which would be 230 games. Worked out to be a nice number. Our standard deviation is the square root of NP and Q. So square root of 460 times 0.5 times 0.5. We'll round it to 10.7 games. Okay. So for random groups of 460 overtime games, the mean number of wins is 230 and the standard deviation is 10.7. The values separating numbers of wins that are significantly low and high would be plus and minus 2 standard deviations from the mean. So significantly low, we take the mean, which is 230, and then we're going to subtract 2 standard deviations. If we do that, we'd have 208.6 games. And then significantly high, take the mean again, and add 2 standard deviations, which would give us 251.4. So if you have between 208.6 and at most 251.4, anything in the middle would not be significant. Anything less than 208.6 or more than 251.4 would be high. Okay. So if we look at the last part of the question, the result of 252 games would be significantly high because it is greater than the highest value we found. So 251.4 is the barrier for being significantly high. 252 is just bigger than that, so it would be significantly high. Right. Next time we will talk about standard normal distributions. Have a great day, everyone.